Hello everyone and welcome! Today we're going to be diving into building a running platformer using the MapleStory World's game engine together. To help you follow along, we'll be exploring the running platformer sample world that MapleStory Worlds provides. And besides this video, you'll also have access to a detailed lesson plan and the sample world itself. And these resources will really boost your understanding, so I heavily recommend you reference these materials as you watch this video. The sample world is especially useful because it includes detailed code comments, so if you need extra clarification or want to dig deeper into any of the code, definitely check those out. Alright, so before we jump into building, let's do a quick demo of the sample world we're going to create. So here is our running platform framework. Let me maximize this. And we can see our best score that is tracked every time we run. Our best score will be tracked and it'll be updated here. We also have our manual showing us how to play. Our spacebar is bound to the jump, and our K key is bound to our use skill action. So we'll close this out and we'll click Game Start, and we're shown a character selection screen. We have two different characters to select from, both with different abilities. So our test character A, if you use our skill, it has the heal 3 ability, and our test character B, if you use our skill, it has a bonus speed of 4. So let's select the heal character, and if we get started, we have different items. We have the turkey leg that restores our stamina, and then we have the little star that gives us a little bit of a speed boost. And we have coins that we're collecting here. At the top, we can see our score, as well as our stamina bar going down slowly. If we make contact with an obstacle, we can see that our stamina gets decreased significantly. Again, if we just eat the turkey leg, we can see that our stamina does go up. Also notice the background changing as we run through this dungeon. And our tiles are also changing as we run. If you press K, we can see that our skill is used and we have restored our stamina. And we just died, but you get the idea. This is our current score. If we had exceeded our high score, then our main menu would be updated. So we have, in our main menu, we still have 5,470 because I did not beat my high score. And this is the game that we're going to be building today. So as you just saw, a running platformer is all about keeping your character alive as they continuously run and jump across platforms. So to complete this game from start to finish, we'll be working through several key processes. First, we'll learn about logic, and these logic scripts will set up our world environment and control the overall game flow. We'll then create a scrolling system and procedural map generation. We'll build an endless map using object pooling for optimization purposes and configure our player character with the life or stamina system and UI. We'll place obstacles and items and adjust them based on difficulty. And finally, we'll implement a data storage system to save user records. So as our first step, let's start by setting up our most important foundation, our world environment. For a character to run on the floor and jump into the sky, we need some sort of physics laws that exist in the real world. But what would happen without a physics system? Well, your character would either just float around in midair or fall straight to the floor. Not exactly what we want for a running platformer, right? So in MapleStory Worlds, for characters and entities to properly handle collision and gravity, we need to apply the physics system that MapleStory Worlds provides. This is what lets your character land properly, jump, and collide with obstacles. But before we apply this physics system though, let's understand the 3 map modes that MapleStory Worlds offers: Maple Tile, Rect Tile, and Side View Rect Tile. So starting with Maple Tile, this is our classic MapleStory tile system, and it uses preset tile sets provided by MapleStory Worlds. And these tiles are designed when you place them to flow smoothly together. And we do have a tutorial on this in our MapleStory Worlds tutorial videos. So do check out our Pro Mode series for a deeper dive into how exactly these tiles are stringed together. But this is best for traditional MapleStory style games, but there is a limitation where once these tiles are placed, you cannot easily create or destroy these tiles in runtime. Next, we have our Rect Tile, and this is going to be your top-down view that supports 8-way or 8-directional movement. And the tile placement will be based on a grid system, and again, it'll be a view from above. We can designate certain tiles to be impassable or passable, And depending on that setting, the player will either be able to walk across those tiles or be blocked from movement. And lastly, we have our side view rect tile. And our side view rect tile is going to be your side-scrolling game similar to our Maple tile, and it uses custom tile images instead of the presets. So this means that you can use or import your own resources and create your own tile sets to use as the tiles for your world. And similar to the rect tile, it is grid-based, so you'll be placing tiles based on a grid. And the key advantage here, and this is similar to the rect tile, and the rect tile also shares this advantage, but it allows dynamic tile generation and removal. So at runtime, you can generate tiles, you can remove tiles, and you can do kind of a more procedural generation flow if that is what you like. So depending on which type of tile system that you're using, whether it's Maple tile, rect tile, or side view rect tile, each one operates based on a different type of physics component. So if you're using Maple tile as your main system, it'll be utilizing rigid body. If you're in rect tile, it'll be using kinematic body, and if you're in side view rect tile, it'll be using side view body. So keep this in mind that you do have to attach the proper type of physics component depending on which type of tile you're utilizing, whether it's Maple tile, side view rect tile, or rect tile. And if you're switching between these different types, make sure that you're enabling or disabling the proper components to make them function properly in that tile type. Among those three different types of tiles then, which tile type do you think our running platformer game will be best suited for? Our first requirement for our running platformer is that it has to be a side view perspective. So that immediately eliminates our rect tile as an option because that is a top-down view. So it's either going to be tile map or side view rect tile. The second requirement is that we need dynamic floor generation. Our runner is an infinite runner, so we need to procedurally generate tiles, and the player needs to be able to walk on top of those tiles, and those tiles have to be destroyed and created at runtime. So that also eliminates our Maple tile. That leaves us finally with side view rect tile as our ideal choice. The final requirement is that we need independent floor function. So we need different floors with specific functions, not just visual tiles. So for example, floors that are destroyed when they go off screen, or floors that speed up the character. So because we're doing such dynamic behaviors to these tiles, moving them, speeding them up, destroying them, rather than manipulating the grid itself, we're going to stick with our side view rect tile map. However, we're actually going to be utilizing the physics rigid body component and building our own physics calculation system using this physics rigid body component. So our implementation is actually going to be using none of these three, the rigid body, kinematic body, or the side view body. And we're actually going to be utilizing our MSW Maker's physics engine to build our own player controller around this physics engine. So to do this, there's a couple of setup steps involved. We're gonna navigate to our default player, and we're gonna take a look at all the components that are associated with our default player by collapsing all of these and doing kind of a bird's eye view of all of our components. First up, we're going to remove all three of these, the rigid body, kinematic body, and side view body, because as I mentioned, we're not going to be utilizing any of these. So let's remove these. Remove this component. And notice that we are getting an error or a warning here that this component is defined in a base model and cannot be removed. This means that our default player entity is based on a model and our default player entity is an instance of that model. Any components that exist on the base model cannot be removed from the instances of the model and must be removed directly from the base model itself. But we can manually do this by going into our base environment, opening up our native model folder, and scrolling down until we find our player entity. And this is going to be the model that we need. So we will collapse all of these again. And from the model, we're going to remove our rigid body component. We're going to remove our kinematic body component, and we're going to remove our side view body component. We're also going to be building our own player controller. So let's remove our player component and let's remove the movement component. The reason we've removed all of that is because, again, we're building our own physics system, and these built-in default physics systems will kind of get in the way. now that we've got those default components removed, let's add in the base components for physics. So we'll add our physics rigid body component. And this will give a certain weight and gravity to the character. So this will allow the character to fall naturally, allows a certain force when jumping, and it acts as kind of a physics engine for this entity. So the main properties that we'll configure here is the body type. So the body type, we're going to use dynamic, but we have static, kinematic, and dynamic body types. And for more information about the differences between each of these, we do have documentation on this, so please do reference that documentation, but we're going to be utilizing dynamic body type. And we're also going to need to take a look at the mass. So the mass will adjust the weight of our character, and we're going to collapse this component out, and we're going to add our physics collider component. And our physics collider component is going to be able to detect collision boundaries for this entity. So it creates kind of an invisible hard shell, so to speak, around this character and prevents overlapping with other objects. So there will be a physical contact with other entities with rigid bodies. So these two values, our box size and our collider offset, will be what determines the shape and position of our collider. So if you take a look at our player, we're going to place it to hierarchy just so that we can take a look at our physics collider component. And if we edit this collider, we can see the box size as well as our collider offset. So our box size, if we increase it or decrease it, we can see that we can modify the range at which our player will be able to take damage from. So this will come in handy, especially when we crouch and we need to decrease the box size to the crouching position. Same thing with our offset, we're probably going to be modifying our offset position as well. So these two settings is going to be what we're going to be manipulating the most with our character controller. So we're going to apply the default and we're going to just delete. Okay, so now that we've got our player set up with our physics systems, let's go back and let's also add the floor now, because our player has to fall onto something and it has to interact with the floor. So let's create a new empty entity. Let's name this floor underscore 1 for now. And then let's add our sprite renderer component. And as the name implies, this will just simply allow us to render a sprite onto our screen. Let's go into our resource search here. Let's search for a cloud. And then let's set the category to platform. And now you can see a list of all the platforms that we can interact with. Let's use, let's say maybe this one. And let's copy the RUID by clicking this button here. And let's paste that right into the RUID field there. And hopping back into the scene, we can see that we have updated our sprite. Let's add our physics rigid body component, and adding this will also add the physics collider component. Now, if we look at the player, physics body type we set to dynamic because we want it to be moving at runtime. The floor, however, we know is never going to move. So we're going to keep this as static. So static essentially means that it has infinite mass, it will not move, it cannot be moved. So we'll set this as static. We'll double check the collider to make sure that it is properly set up. And then we'll check the client only option to make sure that we render or we calculate the physics only on the client side. We can of course set it to the server side calculation if we want, but given that this is a single player game, we're going to keep this as client only. And same thing for the player. If you look at the physics collider component, we have set the client only option here toggled on. So the last thing, to enable the physics systems here, if we press play right now, we'll see an error. And it says that physics simulator component does not exist on map 1. So we're going to add that to map 1. Physics simulator component. And this will allow the calculations to actually execute. So if we press play now, we can see that our character had fallen onto the cloud and it's able to fall. And we're going to add our actual jumping and the tile movement and all of that stuff in future sections. But for now, this is all we need. So far, we've learned about the most basic environment settings for creating a running platformer game, and we understand now the map modes, as well as the physics system. Now our character is ready to realistically run on the entity scrolling floor that isn't just a simple tile, but it will have its own independent functions and various scripts attached to it that will allow it to function in the way that it does in our runner game. However, just because this physics engine runs well doesn't mean that the game is complete, right? So as a character runs, the score needs to increase, UI elements like health bar must display on screen, and data such as spawn item probabilities and scroll speed, things like that have to be managed. For a first-time developer, you might feel the urge to create a bunch of meaningless entities that aren't even visible on screen and attach a bunch of components to them to control other entities. But this ends up messing up your code later on and makes project management incredibly difficult. So rather than that, in the next section, we'll learn about logics, which is going to be the core of our various management functions. And it's a powerful core feature of MapleStory Worlds that will solve these problems. So before diving into this next section, let's clearly understand the difference between components and logics. Both are scripts, but both have different functionalities and different use cases. So components must be attached to a very specific entity. So if we create a component by right-clicking on my desk and clicking on Create Component, and then naming our component Hello Maple World, for example, from any entity, we can click on Add Component and associate this component with that entity. So this component will then control and manage this entity, and it requires an entity to exist and function for this component to actually work. So when you first start creating a game in MapleStory Worlds, then you might wonder, okay, components have to be attached to entities. Then for every function in my code, should I be creating an entity? For example, should I be creating a score entity to manage scores and a UI entity to manage UI? A normal component must be attached to an entity to perform any action. So to run a function, you might think about creating a dummy entity that's invisible. But this can end up unnecessarily wasting performance. As your game development continues and the project becomes more complex, it becomes so much harder to manage all these components and dummy entities that you're creating. This is where logics come in. Logics in MapleStory Worlds are different. It's designed to operate globally within the script itself without being dependent on any one entity. So in this section, we're going to be learning how to use logic effectively and control games much more conveniently. So logics, as we mentioned, are an independent unit. They're not dependent on any entity, and it exists as a standalone script. Logics will generally manage the entire world globally. And again, no entity attachment is required. So let's, for example, create a logic script within our workspace. So when we create a logic in our workspace, we can then globally access any properties or methods contained within the logic file. In our project, we've got a couple core logic files. We have our game logic, we have our dataset logic, and we have our UI manager logic. All three of these will be critical to our overall flow of the game. Having these globally accessible logic files now eliminate the need for dummy entities and don't waste any entities on invisible managers. They allow centralized control, which is perfect for managing game-wide systems, and they're performance efficient and requires less entity overhead. So what exactly is a manager? A manager is generally a logic file, and it's an administrator that comprehensively manages specific data or functions in your game. It provides centralized control of related systems and allows communication between the different components. So for example, in our dataset manager manages all game data, items, characters, and stages. Our UI manager manages all of the UI elements and their states. And the game logic manages the overall game flow and the rules. So why are we using logic for managers? Logics, as we mentioned, are globally accessible by nature, which is a perfect fit for a manager role where multiple components across various maps in our world will need to access this logic file. Having our managers as a logic file also eliminates the need to find and reference different types of entities to access the functions within our managers. So let's take a peek into our game logic. So again, the purpose of our game logic is to control the overall flow of our game from start to end and the state changes in between. So the first thing we'll notice is in our onBeginPlay, we have an initialize function. In our initialize function, we sequentially initialize different parts of our game. So we connect references for our scrolling controller so that we get a reference to the scrolling controller. We also initialize our data, our UI manager, our object pool. We also set the score to 0 and set the HP to 100. So a lot of initialization steps happening in our game logic. And this is important because some of our logic depends on a sequence of execution. For example, before UI can load any kind of score or data, it first has to be loaded. Let's now move to our game start method, which is called when the player presses the play button. And our game start will then initialize our game state so that it can be ready to begin the game. It displays the required UI. It'll initialize our game state. For example, it'll set our default scroll speed. It'll register and request a stage change. It'll set the score to 0. It'll reset the HP to 100. Then it'll call the relevant UI so that we're showing the mobile controls, player info, and the countdown timer. There's a couple other UI and skill initialization steps, but essentially, the game start will just prepare our game and reinitialize and reset all of our UI and our data back to its initial settings so that the player can begin from a fresh slate. From here, we'll move on to our game end method. And the core logic here for our end main game is to first set the flag for ending our game so that other game logics or components know that the game has completed. We're going to set the player visibility to false so that we can return back to the main menu. And then finally, we're going to show the result UI. Then moving to the health score management, we have our add HP method, which will allow global access to the ability to subtract or increase our player HP. So we're passing in a certain value and we're going to increase our HP value by that amount, or decrease if this value is negative. If our HP happens to go below 0, we're going to end the game and begin our end game sequence as we just saw. In between the game starting and ending, we have our stage changes. And we saw as we played the game, the background changing between the different tile sets and the backgrounds. And we have our stage change that will manage that. So in our stage change, we're going to increment our stage number and do a modulus with the maximum stage resource count and cycle kind of between those stages. So this is kind of a circular cycle that will infinitely cycle between our various resources. The final major logic to cover in our game logic is our load data method, which will load in our data for getting our maximum score. If we don't yet have a value for our best score, we're going to initialize our score to 0. Otherwise, we're going to set our score to the value that we returned. We're going to assign the final value to our best score property. And down here, we have our onSync property, which is going to be a listener for whenever values change on the server side. So this best score is a server-side property with the sync tag associated with it. So if you scroll all the way up to our properties, we can see that our best score has a sync tag associated with it. And what that means is anytime this property is changed on the server side, it will notify the client side that this value has changed. And we are using our onSync property event that is automatically called whenever this happens. And we're going to check for the best score value. And whenever this value is changed on the server side, on our client side, we're going to update our UI with that new value. Now, if we have a way to load our score, we of course will also need a way to save our score. So that's what our save score method is going to do. It's going to take in a score value. It's going to grab our my data key from our global data storage, and it's going to set the best score value with the score that we passed in. Now, a quick note is that at the moment, we only need for our player a best score value. So there isn't too much data to load and save, so we consolidated that logic into our game logic. However, if you had more user data to load in, you might want to consider separating out this logic into its own logic file. So for example, we might want to consider creating a new manager and naming it something like user data logic. and bringing out the logic from our game logic for loading and saving our best score data into its own manager so that we can consolidate different user data in one place instead of having it inside of game logic. But because we don't have that much data to load in for this particular example, we've just saved it in our game logic. So with our game logic, we can, for example, let's say my component. Let's say we had an entity somewhere in our world. Let's create a new entity and let's attach our my component. And if we open up our component, we can on begin play, we can do something like game logic, add HP, and we can do 10 HP. Or we can call game logic, add score of 100. And as you can see, we can globally access from our component the ability to add HP or add score or any of the other globally accessible methods from within our game logic. Moving on, let's hop into our next manager, our UI manager logic. So let's double click to open this up and take a look. Our UI manager logic is a central hub for all of the UI in our world. So if we look down into our connect refs method, we can see that we are storing references to a bunch of different UI paths. And this is to allow different components to globally access and modify the game UI state, not by individually referencing or individually searching for any one component or UI element, but rather accessing by action type. So for example, if we want to show the mobile joystick, all the caller needs to know is that we are showing the mobile joystick and we don't need to individually reference our UI group so that we can enable that. Or showing our character select pop-up, we are grabbing the reference to our UI character select window and enabling that. So this allows us to have our UI manager logic handle various UI actions and delegate the behavior to the respective UI controllers and have global access to these types of functions and the various controllers they're in without having to manually reference the various components or controllers. We also have the ability to not just activate and deactivate entities, but also to update entities. So for example, update title best score takes in a score and updates our best score value. Similarly, we have set score text, which will set the score value in game, and we have our HP slider value, which will set the HP UI slider. So there's a separation of concerns happening here between our game logic and our UI manager, where our game logic manages the game data and the overall flow of the game, and the UI manager manages the activation of UI, the deactivation of UI, and update of various UI elements. Next up, we have our dataset logic. Let's double click to open this up. Our dataset logic, as the name implies, is in charge of managing our game data throughout our world and making access to that data easy and globally accessible, just the same as our other logic files and other managers have done so far. So here's the problem that we're presented with. We have a lot of different types of data. We have item stats for pickup. How much should you gain from these items, or skills or pickups? What types of skills should you have? How many characters are there? How many stages are there? How many tiles are there? All of this types of data needs to be managed and stored, but how do we actually manage that data? Well, in MapleStory worlds, we utilize what's known as a data set. So if we look into our data table folder, we can see we have a bunch of different data sets here. And these are essentially CSV files that we can modify. So if you've ever opened an Excel sheet before, you can notice a similar pattern. So in our item info sheet, for example, we have various columns for our items that can be picked up in the game. We have coin items, we have health items, and we have booster items. Our coins have a value of 50, our health has a value of 20, and a booster has a value of 1.4. We have various spawn rates, so the chances that these items can spawn into the world. We have the RUID for the image associated with this item. And then we have the model that we are going to spawn in and place into the proper item slot. So we have this data collected in our CSV file or a dataset file. And now we need to transition this data into code and into memory. To do that, in our init method, and remember this init method is called from our game manager in our initial game sequence, but our init has an init method for our item info table. So if you look into this method, we can see that we're loading in this dataset name, item info, and we're going to get all of the rows, and for each of the rows, we're going to grab the various columns. So we have our name value, our RUID value, our actual value, we have our spawn rate and our entry ID, and all of these are going to be stored into a row data table, and that data is going to be stored into an item info table by index. So index 1 will be the coin, index 2 will be the health, and index 3 will be the booster. So in this way, we have loaded and converted our Excel table, our dataset table, into data that is loaded and cached in memory. So this makes accessing our data fairly easy. We have our my component here that we've created just as a test, and it's associated with our map entity. So if you double click to open this up, we can add a onBeginPlay method here. And from within here, we can make sure this is a server only method. And from within here, we can, let's say, log out the health spawn rate. We can do dataset logic, and we can do item info table. And from here, remember that, let's say for the health item, it is index 2. So we're going to do index 2. And we're going to do dot spawn rate, because if we go back to our dataset logic, that is the key that we saved our data for. So we have our spawn rate inside of the second index, and we're going to try logging this out. And if we press play, we can see that we are getting an error, and that's because this should actually be client only. And the reason for that is because in our dataset logic, we are in client space for caching our item info table. So let's replay that one more time and press play. And here we can see that 0.03 does match our item info table, 0.03 for our health item for our spawn rate. We can do something similar where, for example, if we wanted the booster value we can do item index 3 for our booster, and the booster value would be the value column. So we can do value, and then we'll log this out. And we can see that we are getting 1.4, which matches this value here. So in this way, it makes it easy to access and manage our data, and all of our data is stored as data table, and it's very easy to modify these tables down the line, and our data is loaded into our dataset logic and can be easily accessible by other components or logic files. So in this section, we've learned all about the concept and use of logic, which is key to efficiently managing games in MapleStory World. Let's quickly recap all the things we've learned so far. First, without having to create meaningless entities, you can use logic to easily access them globally without being dependent on a specific entity. Second, project maintenance becomes a lot easier by centrally managing roles divided into things like game logics, UI manager logics, user data logics, or dataset logics. Now that you know how to create the core framework of the program, it's time to implement the core functions of our running platformer game. Running platformers are infinite running games where characters run continuously. So how do you make your character run to the right forever without ever stopping? We'll find the answer to this problem in the next section. So in the last section, we asked the question, how do you make it look like your character's running infinitely to the right? This time, let's learn about the core principles of the scroll system. There's two ways to achieve our infinite scrolling map. Either make the character actually move forward, or leave the character in place and move the background and the floor to the back. This approach is known as relative scrolling, where the character stays stagnant on the screen and the background and floor are pushed backwards. So why use this method? Well, if the character moves along the x-axis at a very high speed, so for example, if we moved our character to the right at a very, very high speed, and the x-coordinate value keeps on increasing, this can cause rendering issues or glitching that makes the camera shake. Plus, there's an extra computational cost for the camera to track the character, which can be a very big burden. However, if we use the relative scrolling method, the character only jumps in place, and both problems are solved by fixing the camera at the game's starting point. Now, with the camera and the character both fixed, let's see how to move the background and the floor. MapleStory Worlds already provides a background system that we can utilize to achieve this kind of scrolling effect that we see in the background here. So if you look at our background, we can see that we have a scrolling rate. At the moment it's set to 40, which is why our clouds in the background are moving pretty quickly. But if we've slowed this down to say something like 10, it slows down significantly. So we can use this to achieve that kind of movement feel. But this alone doesn't finalize our movement. Just because our background is scrolling doesn't mean the tiles themselves are actually scrolling. So let's go into our models, and if we right click and place the hierarchy, we have these tile sets. And these tile sets are going to be separately controlled through our scrolling controller. So let's take a look at that next. Under My Desk, and searching the components folder for our tile set folder, and let's double click our scrolling controller. And here is the component that is responsible for moving and managing our tile sets. So the core of our scroll behavior is happening right here in our scroll method. The scroll method is called every frame on our update and is moved at a certain scroll speed. When we pass that scroll speed in, we're going to move our tile parent, and checking the connect reference method here, we can see that our tile parent is going to be the path at scrolling tile parent. So that would be this entity right here. So all of our tiles are going to be childed under this tile parent here. And when we move this tile parent, all children tiles will be moved together. When we check our on update here, we can see that, again, we are scrolling in the negative direction based on our current scroll speed, multiplied by our frame delta. But we also have this validation up here where we check if the game is ended or not. If the game is currently over, we're going to return and stop scrolling our screen. Now remember that we have our game logic manager logic file here. And inside of our end main game method, we have our isEnd flag being set to true. So that is what our scrolling controller is checking for. We have three different types of properties that control speed. We have our current scroll speed, which will be the current value that is actively moving our scroll. We have our default speed, which is going to be the base speed of our scrolling, which is necessary for things like boost that temporarily boost the speed. We need a way to revert back to the original speed, which is going to be this value here. We have our current background scroll speed, which is going to be the speed at which the background is actually scrolling. So if we look in our init, we can see that we have our background scroll speed set to the config background scroll speed. So this config file contains a ton of different base values and values that will not change throughout the game. And we have our background scroll speed, which is going to be the default background movement rate. So the background scroll rate value that we saw right here in our background, the scroll rate value is going to be modified to the background scroll speed. And we're going to cache the current background scroll speed again to the background scroll speed as well. So for example, we have our item logic, which manages our items in our game. And whenever we collect a booster, for example, the speed booster, we can see down here that we are modifying our target scroll speed by the scrolling controller's default speed multiplied by the boost item factors. And here's that pattern again for our dataset logic. We're grabbing the third item and we're grabbing that value here. So if we go into our data table again, item info, this third is going to be the booster value, and we're grabbing this 1.4 here. So that will be what is loaded into boost item factor. So we are multiplying our default speed by our boost item factor of 1.4. We're going to similarly modify our target background speed by the config background scroll speed base value by our boost item factor of 1.4, and we're going to set both of those by our scrolling controller's set scroll speed method and the set background scroll speed method, which is going to modify those current scroll speed values for both the tile scroll as well as our background scroll. Then, once the booster timer is done, we're going to reset the scroll speed back to the default speed and reset the background scroll speed to the default speed set in our config. So we saw that as our game progresses, the background also changes. But if we look at our scrolling controller, we can see that we don't have a method for changing the background. We do have a method for setting the background, where we change the background based on the RUID that's passed in, but there's no controller for actually managing the timing of that background change. Well, that's actually managed in our game logic. So if you remember, our game logic is responsible for handling the overall game logic flow. So our game logic is actually handling the stage changes, where the stage changes will trigger the background change as well. So in our game logic's update, we can see that we have our stage timer, and our stage timer is going to last a certain duration. And as soon as that stage timer hits 0, we're going to trigger a stage change, and we're going to reset the stage timer to the config stage change time. So if we hop into our stage change time in our config file, we see that at the moment it changes every 10 seconds. So every 10 seconds, there's going to be a stage change. So hopping back into our on update, we can see that we have our stage change method, and inside of this method, we have our current stage being, again, as we mentioned before, being cycled through our different stage resources. So our stage resources will contain all of the different data for our stages. So if we hop into our stage render info, we can see that we have 3 different types of stage information. If we look at our dataset stage resource count, if we hop into our dataset logic here, we can see that we have a stage render info table as well as an init stage render info table method. So inside of this method, we are grabbing our stage render info from that table. So if we check our maker again, we have the stage render info table that we are grabbing by name. And for each of those data sets, we are grabbing our row count, and our stage resource count is going to be that row count. So this would be a value of 3 because we have 3 different types of stages. So going back to our game logic, we're going to be looping through 3 different resources, and we're going to cycle over and over again through those 3 different types of resources. So once we get the next stage value, we're going to call change background based on the current stage. So if we hop into our scrolling controller again and check our change background method here, we're grabbing the game logic's current stage, which remember was updated in that same method. And we're going to grab our dataset logic's stage render info table, and we're going to index the current stage and grab the background RUID property. So that will be this value right here. And that will change the background to the RUID for that background. So let's play the game again here and pay special attention to the background as it changes. There's our first background, our second background, and we should get one more background in almost 10 seconds, and there we go. There's our final background. So we are cycling through all three different background types, and in just a moment we should get, yes. So those are our three different background types that we are scrolling through. So at this point, we've taken a look at our relative scrolling technique, which pushes the background and the floor backwards while keeping the character fixed on screen. We've also learned how to cycle stages infinitely using GameLogic's timer with the modulo operator. But if you take a look at actual infinite running games, the patterns of obstacles and stepping stones appear every time you run. So next time, instead of drawing tiles endlessly, let's learn a procedural map creation technique that creates various chunks of terrains in advance, kind of like Lego blocks, and randomly connects them endlessly. If you've ever played a running game before, you've probably seen this endless generation of stepping platforms. The core of this section is dedicated to the procedural generation method. Now, it might sound like a difficult concept at first, but let's check out what procedural generation actually means for our project by looking at a simple example from our sample world. So let's start our game, and let's pay special attention to this exclamation point here. As our tiles reach this exclamation point, you can see that they're being destroyed. And on the other side, we can see that new tiles are taking their place. So this cycle is being repeated, where tiles are being destroyed and being replaced by new tiles. But there's an important problem here. Let's assume our running platforming game has not only the first and second floor, but also a third floor. If tiles are created haphazardly, you'll run into a problem where the character suddenly can't jump onto the first floor to the third floor. So we create some logical spawning rules that dictate when and how those tiles are created and how they're connected together. So if the last point of the previous tile ends on the first floor, the next tile should start on the first floor. So there's 4 main steps to achieve our procedural generation here. The first step is going to be to create a chunk map, and a chunk map is going to be a collection of tiles and stepping platforms under a single parent. Next, we're going to create a dataset that manages our various floors and has a link to the various chunk map entities. Next, we're going to code some logic that properly spawns the correct type of floor depending on the last floor that was spawned in, so that we properly connect these floors together. And finally, we're going to implement a dead zone, where tiles that enter into this zone are destroyed so that they can be recreated at the end. So returning to our first step, we have our chunk. So a chunk again is a series of connected tiles under a single entity. We have multiple of these floors grouped together so that they can be spawned together, and each of these chunks have a fixed width so that we know exactly where the next position should be at. We're going to need to have a way of recording which floor our chunk begins on and which floor our chunk ends on, so that when we connect 2 chunks together, we're not creating a disconnect, and we are making sure that the player can actually jump onto this next tile. So for example, each chunk has a width of 10, so we know that the next chunk should be placed exactly at 10. And this chunk's pivot point spawns directly at the very left side of our chunk so that we can connect these 2 pivots together from the start to the end of each chunk. So in this case, because this chunk ends in floor 2, the next chunk should start on floor 2. Once we've created our chunk, we're going to right-click and save our entity with our tile parents. Now, once we've created our chunk, we're going to right-click and we're going to create what's known as a model. This has already been created into a model for you, but if you wanted to create more tile sets in the future, you can use these tile sets as a basis for creating your own tile chunks. We have this purple dot here, and this purple dot is going to be where our second floor is at. So this is our first floor, this is our second floor. So we know exactly the position for our floor. So for each of the chunks that we create, we're going to store that data in our tileset info data table. So we have our first chunk with the first floor starting on 1 and the last floor ending on 2. So if we double check this first tile set, we indeed have the first floor starting on 1, last floor starting on 2. The next one, we have 2 and 1 start on 2, end on 1. And if we check here, we start on 2 and on 1. And so on and so forth. The entry ID contains the model ID for each of our tile models. So if we right click any of our tile set models, we can copy this entry ID, and that is what we are pasting into this field here so that we can spawn these in and reuse this same model over and over again. Remember that all datasets are managed and loaded from our dataset logic here. So all of our tile information is contained within our tileset info table. And we have an initialize method for our tileset info table as well. Hopping into this function, we can see that we have our tileset info data table being loaded in, and all 3 of our columns, first floors, last floor, and entry ID, being loaded into our row data and stored into this table. And it'll follow the same access pattern as we saw so far, so that this data can be accessed globally. So next up, we have to code the logic for our tiles from within our scrolling controller. So in our scrolling controller, we have our spawn random tile method that has a random number that we're grabbing from our get random tile number here. And we're going to grab the proper tileset data based on whatever the last floor was. Meaning, if the last tile chunk was tile chunk 1, the last floor was 2. So the way that our tiles floor info table in our dataset logic is structured, each of the floors are going to be split into their respective first floors. So whatever they begin with, 1 or 2, in this case, because we only have 2 different floors at the moment, that will be the index for our floor. Then this will return another table. So we have our tileset floor info table. So let's say the last floor was 1. We have a table of all floors that start with 1. Then from here, we're going to randomize a random data from those chunks, and we're going to return the selected tile number. Once we have our random number, we're going to spawn that tile. So if we hop into our spawn tile, we're going to get the tile from our object pool. We'll get into that later. But for now, let's just imagine we're just spawning a new item in. And we're going to cache our last tile floor to the tileset number that we're about to spawn in, last floor value. So that will be the last floor value here. And that will govern the next tile that is spawned. Whenever we call the random spawn tile again, it will be based on that last floor tile value. And then we're going to grab the spawned tile's position and set that position to the current spawned number. So however many tiles have been spawned so far, multiplied by 10, because we know that each chunk has a width of exactly 10, and we're going to spawn it exactly at that pivot point, that multiple of 10, so that we have no gaps in between our tiles that are being spawned in. And then we're going to set our last spawn tile number to the current tile set number that we just spawned, and then we're going to call init on that spawn so that we reinitialize our object. In this way, we've created a specific set of rules. While it is random, it is controlled random, meaning that we can never have a completely random tile that will make the game unplayable or force the player to lose every time. So remember that we have our scrolling function from section 3 that scrolls our tile parent to the left while the player stays stagnant in place and the background moves. So we create the illusion of movement by scrolling the background and the tiles to the left. And our final step is going to be implementing our dead zone. So if we hop back into our maker here and we take a look at our dead zone entity, we have our component attached called tile dead zone. But before we open that, this component will destroy any tile set chunks that enter into this trigger range. So we have our collider here that we've set to this really tall height so that any tile that enters in will be destroyed by this tile dead zone so that it can be respawned back at the end of the line. So double clicking on this script here, we know that this tile dead zone is always going to be off screen. And we have this handle trigger event, which is an event that is sent by this trigger component anytime another entity enters into this trigger range. And we're going to grab the opposing trigger body entity. We're going to grab the collision group of the trigger body entity. And we're going to check if that trigger group is a ground group. So if we look at our trigger here and we open up our collision group matrix, we can see that our trigger component is set to dead zone. But if we look at our tile, we also have a trigger component, and this is set to ground. So we have to make sure that our tile dead zone and our ground groups are collidable, and that will be determined by the matrix here. So let's open up this panel here and hop into the matrix. And we can see that our dead zone and our ground is checked. So the ground is interactable with our dead zone. It's a good idea to double check this collision group to make sure that you're not having any unnecessary calculations going into entities that you don't really need to be calculating collisions for. So we'll close that out, hop back out into our tile dead zone component. And again, we're going to check for our trigger group to make sure that the opposing trigger group from the perspective of our tile dead zone is the ground trigger group. And if so, we're going to destroy the entity. And we're going to get into object pools in just a moment. Object pooling is a optimization step, but let's just imagine that we're just destroying this entity for now. And then after we've destroyed this entity, we're going to spawn a random tile again and repeating that same pattern. And that's procedural generation. So through this section, we've implemented a procedural map generation system that uses dataset to randomly connect chunks with the right number of floors and removes chunks that go off screen through the dead zone. But this seemingly perfect endless running map actually hides an invisible time bomb, so to speak. Our game is constantly creating new heavy chunk models throughout the character's run and constantly destroying them whenever they hit the dead zone. From the game engine perspective, creating new entities and completely destroying them each time puts a huge strain on memory and device performance due to garbage collection issues. So if playtime continues like this, a sudden lag is bound to occur at some point. So instead of completely destroying the tiles that are off screen, we could just hide them out of sight and recycle them later when we need those same tiles. And that's where the object pools that we've been seeing throughout our code comes into play. Think of them kind of like a cabinet for storing empty bottles. We're gonna take them out, fill them, and use them for what we need, and then we're gonna store them back into that cabinet for use later. So it's an optimization technique that allows the storage and reuse of entities rather than constantly destroying and recreating them. So we learned about the infinite scrolling system in the previous section. The current implementation works like this. When a floor tile touches the dead zone, the tile is removed and a new chunk map is created. A problem can arise here though. As a feature of the infinite running platforming game, you have to continuously create chunk maps. However, the creation and deletion of these new tiles every time can cause performance issues over time. So in this section, we're going to learn about object pooling techniques and how it can solve this problem. So think of object pooling kind of like a recycling warehouse. Imagine empty bottles that are stored in a warehouse and reused as opposed to just being thrown away and recreated every time. After you finish drinking your soda, it's reused to fill it with orange juice. In the context of our infinite scrolling, currently, when a tile reaches the dead zone, it is completely destroyed and new tiles are being recreated from scratch every single time. This repeated creation and destruction of entities causes a memory strain over time due to something called garbage collection. The object pool method then creates tiles at the start of the world. When a tile leaves the screen, it's deactivated rather than destroyed and stored in that quote-unquote warehouse. So when we need a new tile, we take one from this warehouse and we just set the enable status to true and reuse it. Because we're just reusing an entity rather than destroying it, there isn't any repeated creation or destruction, and ultimately leads to better memory efficiency. So let's start learning about how object pool is actually used in earnest in this project. Object pooling is managed through a logic file. So we can see here we have object pool logic. And the reason we're utilizing logic as opposed to a component, as we learned in the beginning of this course, is that it allows easy access and use of the object pooling system from anywhere in our world, meaning anywhere in our various components or other logic files. This allows global functionality and fits this object pool's purpose. We need to be able to access this pool from anywhere in any component. So let's open up our object pool logic and take a look at what's going on. Up at the very top, we can see that we have two different types of pools. We have two tables here. We have a tile pool and we have an item pool. And we're going to see that our pools is being utilized for both the tiles as well as our items. We're going to focus right now on the tiles. So the purposes of these two pools, if we remember, is to reuse and recycle the various tile set objects or item objects so that we can continuously just recycle those entities as opposed to destroying them. So for our tile pool, we have 5 different types of tiles. Going back to our maker, we can see that we have 5 tile sets. Tile set 1, 2, 3, 4, and 5, as we saw in the previous section. So our tile pool data structure looks a little bit like this. We have 5 different indices, and each of these indices is going to store a different type of tile. So in this first index, we're going to store tiles of type 1. So back in the maker, that will be this tile here. So we're going to keep creating and storing these tiles so that they can be reused from this pool. Tile index 2 then will store tiles of type 2, index 3 of type 3, and so on. So we're going to be adding and removing tiles from this pool so that they can be reused in our game. So how do we actually retrieve a tile from this tile pool? Well, we're going to scroll all the way down to our getTile method here, and we can see that we have an input parameter of tile number. So this tile number is going to be the tile index type we're actually going to want to retrieve from. So that will be, if it was 1, we're going to be retrieving from this pool. And we're going to floor that number to a round integer to make sure that this isn't a decimal. And we're going to make sure that this is a round integer number. Then we're going to validate our pool to make sure that that table at that index is actually initialized to an empty table. And then we're going to have 2 scenarios. Either there is a tile in the pool and we're going to retrieve that tile. Otherwise, we're going to create a tile because our tile pool is empty for that tile pool index. If our tile pool is empty, then we're going to grab the entry ID from our dataset logic's tile set info table. So hopping back into our maker, that will be this tile set info table here. And we're going to be grabbing our entry ID column. This column contains a model ID, and that model ID is referencing these tiles here. And then we're going to grab the name of our tile, and that will be model underscore tile set 0 concatenated with our tile number. So each of our tiles has a preset prefix, model underscore tile set 0, and then 1, 2, 3, 4, and 5. So we're going to concatenate that prefix with our tile number. And then with our entry ID and our tile number, we're going to spawn the model with the name at a temporary position under a temporary child entity. Then we're going to return that tile that we just created. If the tile already exists, it's a little bit more simple. We're just going to grab that tile at that index, and we're going to remove that tile from our tile pool, and we're going to enable that tile so that it can be used and return our tile. So now that we've got our tile, we've completed using it, we want to return it to the pool. For that, we have our return tile method here. So return tile is going to work kind of the opposite of our get tile method. We have our entity that we want to return, and we have our get tile number method, which is going to return us the number based on the corresponding name. So if it's model underscore tile set 02, it's just going to grab that 2 and return that number string. Once we got that tile number, then we're going to, again, validate to make sure that that tile pool at that index actually exists. If it does not, we're going to initialize it. And then we're going to insert that tile at that index with the entity. So we have effectively added this entity to the tile pool at whatever index, 1, 2, 3, 4, or 5. Finally, we're going to disable the entity to make sure that it's not visible and it's not actually being used. So now that we know how our object pool actually works, let's return to our tile scrolling to see how the object pool is actually being utilized in action. Going back to our scrolling controller, we have our spawn tile method. We've already covered this and we know what it does, but we're going to re-highlight this spawn tile get tile method from our object pool logic. So we're passed in the tile set number that we want to spawn in. And again, this is going to be an integer value of 1 to 5. And we're going to pass that integer into our get tile method, which is going to return the tile based on the corresponding pool. Then as we learned, we're just going to go ahead and initialize and set up our tile so that it works. Once we're done utilizing the tile, that will be when we enter into the tile dead zone. And we've already looked at the end here where we check for the trigger group to make sure that it's ground. And we had kind of imagined that this tile is being destroyed. But instead of that, we're going to instead call our return tile method that we covered, and we're going to return the trigger body entity's parent. So if we look at our model here, we have our trigger component attached to the child entity. So that will be tile01 or tile02. So these two entities here have the trigger component, but the actual triggering entity isn't the entity that we want to return to the pool. It will be its parent entity, which is this parent model underscore tileset01. After returning the tile to our pool, we're going to call scrolling controller spawn random tile to repeat the process. Now, a very important caveat to remember, and this is a very common mistake that happens in object pooling, is forgetting to initialize reused objects. Tiles from our object pool aren't brand new. Previously used tiles have a state attached to it. For example, a tile with a coin previously on it. If it's not reset, then the coin will be missing when it's reused. So to handle this issue, we're going to, in our scrolling controller, we have our initialize method, which will make sure that our tile is reset back to its default values and set up based on the parameters that we actually want for this tile. So when we're returning to the pool, we're going to reset everything. And then after we return to the pool and we're using it again, we're going to initialize everything with the value that we want. If you hop into our tile set method here and look into our init method, we can see that we have all of our initialization steps, including returning all the items and spawning new items and setting up everything for our tile so that it actually contains the entities that we want and set up with the values that we want and doesn't contain any values from the previous time we've used this tile. So what is the final result of utilizing our object pool? Well, visually, it looks exactly the same. However, behind the scenes is operating much more efficiently. Before, without object pooling, we were creating a new entity every time we needed it, and spawn service was being heavily utilized to create new entities. Memory was being allocated and deallocated for new entities, triggering garbage collection frequently. Over time, the performance impact of this constant garbage collection could accrue and become a heavy burden on your game. However, with object pooling now, entities are created once at the start or only as needed, and we're going to reuse the same entities repeatedly. We're just going to toggle them on and off. So there's no repeated memory allocation or deallocation unless garbage collection tasks are being utilized. So this results in smoother and more consistent performance. So to summarize everything we've learned so far, object pooling is an optimization technique that recycles instead of creating and destroying. We learned about object pools that can efficiently manage memory by returning them with the return and retrieving them with get. Now, instead of recklessly destroying tiles that go off screen and creating new ones every single time, the game operates in an optimized way by storing them in storage and taking them out when needed. The endlessly expanding map and scrolling and the environmental elements are now perfectly implemented. But what about the characters that actually have to run in this environment? In the next section, we're going to implement a player character that the user can directly control. So in this section, let's take a look at how our player character and our player controller is actually implemented in this world. And if you remember, we had removed all of the base components such as rigid body component, kinematic body component, kinematic side view body component. all of those components that have default behaviors built into the components themselves, we instead are going to build our own physics systems based on the base physics rigid body component and the physics collider component. Now, in a running platformer, when our character is standing on top of a tile, the character should continuously run and not just idle on top of the tile. And if you remember, our specific implementation is using relative scrolling, so our character will never actually move, it will just jump up and down. So in our default player entity, we're going to search for the avatar state animation component. And within the state to avatar body action sheet, we're going to search for the idle key. And we're going to change the avatar body action from stand to the walk animation. So now when we press play, our character is now walking as our idle. So the animations that we're going to need for our running platformer is going to be the idle, which is going to be our walk animation. We're going to need the jump animation, and we're also going to need the crouch animation. So if we look at our crouch, we have our crouch set up. So those are the three animations that we're going to be working with. So we're going to double check, make sure those are all there. And we're going to also make sure that our idle is set to walk so that the default idle animation is always walking. So if we check our default player in a sample project, we have our custom player controller that we've created attached to our default player. We're going to double click to open up our custom player controller and take a look at what is happening inside of the code for this. We have a couple key components that we're going to highlight and pay special attention to. First, the rigid body. So we have our physics rigid body component reference that we're going to add force to and manipulate to make sure that we are jumping or sliding or moving our character in the way that we want. So we're going to keep a reference to our rigid body, and in our connect references, we have our rigid body attached in our connect references here. We also have the jump force, which is going to be the amount of force that we want to apply to the rigid body upwards when we are jumping. We have the is grounded property, which is going to check for whether the character is actually on the ground. And this will prevent infinite jumping, where if we press the spacebar, it will continuously add force to the rigid body. So we'll utilize this property to make sure that we only apply force when we're currently on the ground. We have our state component, which is going to allow us to manipulate the animation, active animation of our character. We have our invincible timer, where after we get hit for the first time, or after we get hit, we have a little bit of time where we have some invulnerability. And then we have the is hit property, where we will flag whether the character is currently in the invulnerability state. Okay, so let's start with the jump method here, which will actually allow our character to jump. So here's the validation that double checks to make sure that we are actually on the ground. If we are not on the ground, then we're not going to be able to jump at all. We're going to set the rigid body's linear velocity to 0 so that we are canceling out any active movement in the y of our rigid body. And then from that zeroed out y velocity, we're going to apply an upward force in the vector2 up direction multiplied by our jump force. So we have a jump force of 730 at the moment, and that is the amount of force that we're going to apply to our character to move him upwards. And then we're going to grab our state component and check that the current state name is not crouch. And we're going to change the state to the jump state. And the reason we're checking for this is when we're jumping, we still want to allow the player to jump while in the crouch state. So that's why we don't want to change the animation to the jump animation. We want the character to stay in that crouch state so that they can jump while crouching. And then we're going to play a sound based on this RUID. It's just a standard jump sound. And then we're going to set the is grounded flag to false so that we know that the character has jumped off of the ground and we cannot jump anymore because we're already jumping. Okay, so the jump ability heavily depends on the is grounded flag. But how do we know that we're actually grounded on our tile? Well, that's gonna come from our handle physics contact begin event, which is going to be sent from our physics rigid body. So if we look at our default player and we open up our physics rigid body component and we open up the physics collider component, we can see that we have the enable contact event checkbox checked. And this will send the physics contact begin event and the physics contact end events. So these will be events that are sent whenever the rigid body system and the physics collider detects any physics entities entering into their collision range. If we do detect a collision, we're going to grab the contacted body entity, we're going to grab the parent, and we're going to check for a tileset component. So if we look at our tileset chunk here, our tile is going to be the one that is going to collide with our player, and we're going to double check to see if this tile's parent has a tileset. So whatever collided with our player must have a tileset component in the parent entity. And the only case where that would be true is if a tileset has interacted with our player. So if we have contacted with the tileset, we're going to check to make sure that the point of contact is actually below the character. So if it's above in this case, where let's say the character jumped into a tile, then we're going to stop this execution and we're going to return. Otherwise, if the contact happened below the player, then we're going to know that the character has grounded and touched based on the feet, not on the head. And then once we are grounded and we're currently jumping, then we're going to change the state to the move state. So now that we got the jump down, next up, the crouch. So as we play the game again, notice that when we're standing, we have a different shape for our collider than when we're crouching. So whenever we're crouching, we have a different collider shape. It kind of shrinks down into a smaller square. And this will allow us to make sure that we don't collide with the obstacles above. So back in our custom player controller here, when we change state to the crouch state, we're grabbing our trigger component's box size and we're going to change it to the crouch trigger size. So in our config, we have our crouch trigger size set to 0.3 in the Y and 0.4 in the width. And our stand trigger size, we have 0.75 in the Y, so it's a lot taller than our crouching, and the same width. So when we crouch, we just kind of shrink our trigger size down a little bit, and we also offset the trigger by a certain amount. So the standing trigger offset is 0.35, and the crouching trigger offset is 0.12. So crouching, we kind of bumped the trigger down just a little bit. So depending on whether we're crouching or whether we're standing or moving, we're going to adjust the trigger size accordingly. And finally, for our custom player controller, down at the very bottom, we have our handle key down event, where as long as the game isn't over, we're going to detect our keybinds for jumping. So we can see that if we press the space key, we're going to jump using that jump method that we saw earlier. If we are pressing the down arrow, then we're going to change the state to the crouch. And then if we input the K, then we're going to use a skill. We also have the handle key up method, where if we release the down arrow, then we're going to change the state back into move and readjust the collider sizes. Remember when we click on Game Start, we have two different characters to choose from. And each of these characters have different abilities, they have different costumes and slightly different appearances. And when we choose them, they behave in a slightly different way. The data for these characters is stored in our data table. So we'll double click to open up our character info and we can see that we have two characters available at the moment. We have test A and we have test B. Both of these have different values. We have our speed set to 3 for this character and we have a skill ID of 1. If we open up our skill info, we can see that we have a heal and a bonus. So our first character has a heal ability, and our second character, Test B, has the bonus ability. Finally, we have the RID for our character's appearance. Now again, we're going to follow the same pattern through our dataset logic, where if we scroll all the way to the top, we can see that we have a character info table, as well as a skill info table. So the character info table will store our character information, and there is a relevant character info table load method for that. We have a skill info table along with the relevant load method and or init method for our skill info. If we hop over to our UI character select model here, which is the model that actually has the element for our character select button, and if we click on the image, and we can see the costume manager component, and this has a body equip, and this will be the skin color of our character. So this is the RUID that is going to be referenced here, and depending on which character it is, the body equip will be modified to reflect this RUID. Now remember, in our game start, we have various initialization steps where we set the scroll speed, we update the UI, but one of the notable initialization steps to start the game is to reset our character from our custom player controller. So we're going to grab the local player and grab the custom player controller of that local player entity and call the reset character method in here. So let's take a look at the initialization steps for our character. First up, we're going to reset the transform position to 0, 1, 0, and we are going to set the rigid body's type to dynamic. And then finally, we're going to set the character visibility to true, because in the menu, we don't want the character to be visible. From there, when our character is selected, it's going to pass in the selected character ID to the game start method of our game logic. So depending on the selected character ID, we're going to grab the relevant info table. And remember again, this will be this table data here. And we're going to grab the speed entry for that character. So depending on which character we've selected, we will have a speed of 3 or a speed of 4. We're going to pass that to our set default scroll speed that will adjust the scrolling speed of our scrolling tile system. And if you remember, the default scroll speed will be the base scroll speed that the scroll will return to after, say, picking up a boost item that will boost the speed for a little bit and return back to the default scroll speed. So the base scroll speed will be set to whatever the speed is here. Beyond the speed being set, the character also has the ability to perform a special skill on the keybind K. So remember, going back to our custom player controller, inside of the key down event, if the player presses the K key, then we call skill logic use skill. Skill logic is another logic skill that's globally accessible, and it has a use skill method that we will take a look at. Now within this skill logic script, we have two main properties that we're going to highlight. We have our skill ID, which is going to be the ID of the actual selected character's skill. So in the character selection window, it's going to set the skill ID of our skill logic. Again, remembering that skill ID is a globally accessible property that can be set from any component anywhere. So skill ID will be set when we select the character, and then we have our usability flag that will be set to false when we actually use our skill, so that if it's in cooldown, for example, it cannot be used again. So our use skill method, we can see that if the skill is currently not usable, then we won't be able to activate this skill. So if it is usable, then we're going to grab the name and the value from the skill info table from our dataset logic based on the skill ID. And then we're going to, depending on whether the skill is heal or bonus, we're going to call game logic's add HP. For heal, we're going to heal by a value of 20. And for bonus, we're going to add score by a value of 500. Then we're going to set the usable state to false to prevent the skill from being spammed over and over again while in cooldown. And we're going to dim the icon a little bit to indicate that we are currently in cooldown. Our skill data has a dedicated column for our effect RUID. So when we play the skill effect, we're going to grab the skill info table and we're going to grab the effect RUID and we're going to play that effect on the player. Moving into the UI aspect now, if we toggle our UI on and we take a look at our character selection window, we can see that we have an empty scroll layout group that is waiting for character options to be spawned into this scroll layout group. So the entity that is actually spawned in will be our UI character select model. So our UI character select model has a UI character info component that will manage the various elements that you see within our character selection UI. So if we open up our UI character info component, we can see in our UI, we have our initialization method to grab all the reference paths. So we're using getChildByName to grab each of these various entities by name and grab the relevant components associated with that entity. So the name text, the image for the custom manager component, the skill text with the text component, speed text with the text component, and so on. We're also going to connect our select button to the close select pop-up method. After we click this button, it'll call, based on the button click event, this close select pop-up method, and it'll execute the code that we see here. But before we take a look at that, let's take a look at our set info that will set all of these properties that we have initialized here to the values that are passed in as parameters. So we can see the name being set to the name text, the costume image, the costume manager components, custom body equip being set to the RUID. Remember that RUID is going to be the skin color or the custom body equip. And we have the skill names text to be set to the skill and the speed text to be set to the speed. When the close select pop-up is clicked, then we are going to apply our local player's costume manager's body equip or the skin color to the costume image that we set in our set info and set the custom body equip or the skin color to our local player. And then we're going to set the skill logic skill ID to the self skill ID that was also set. And then we're going to start the game based on this character's ID. In our UI character select pop-up, so this will be the actual character selection window, we can see that we are registering our characters, which will spawn our character selection item based on the model ID that we grab here. So we have entry service get model by name, which will allow us to get the model that we want by the name. So we have named our character selection UI character select. So we're going to pass that in and grab our model ID. Then we're going to grab our character table based on the dataset logic. So that will be the character info table here. And then for each of those characters, we're going to spawn in the model and we're going to call that set method. And then we're going to set the skill ID of the character info to the skill ID. We're going to set the name text to the character's name. And then we're going to set the costume body equip to the RUID, the text to the name, the speed text to the speed, etc., etc. And with that, we have our character selection UI and our character information, as well as the character controller itself. So now that the character you create can jump in response to user input, crouch to avoid obstacles, and run as a character with the appearance and skills that you want before starting the game. However, there's a slight issue still, where the game is currently not in a state where it can end, no matter how many obstacles the character encounters or how long they run. The real fun of a running game is the tension of seeing your stamina constantly decreasing and surviving by using recovery items in the nick of time. So in the next section, we're going to implement a health system that will add some fun to our game. Stamina comes in many different forms across multiple different types of game genres. In our game, we want stamina to gradually decrease with time and decrease even further when the player makes mistakes and collides with obstacles. This time, we'll look at the process of implementing the life system that can be used in a running platformer. In this lesson, we're going to be focusing on 3 things. First, the ability to automatically decrease stamina over time. Second, setting the game over when stamina becomes 0. And third, displaying the health bar UI on the screen. We're going to use game logic and UI manager logic that we created earlier. And let's create a structure where internal data changes and on-screen UI are synchronized in real time. So first, let's start with the logic for our health and auto-decreasing. Let's open up our game logic. And if you remember, our game logic controls the overall flow of our game. So here we can see that we have our HP variable. And in our init, we can see that we are setting our initial HP to a value of 100. If we hop over to our config logic, we can also see that we have a maximum HP value of 100. Above that, we have our decrease HP value, and this is going to be the amount that we decrease per second. So every second, we're going to decrease 2 points from our current HP. So hopping back over to our game logic again, if we check our onUpdate method, we can see that we have an auto decrease HP value. So our auto decrease HP value is going to take in our delta, and this is going to be the amount of time that has elapsed per frame. So every frame, we're going to, let's hop into our auto decrease HP method. We're going to add that delta multiplied by our decrease HP value. So even though the method name is add HP, we're actually decreasing it because if you remember, our config value is a negative value. So when we multiply here, we're actually multiplying our delta by a negative value. Therefore, we are decreasing our HP at a rate of 2 health points per second because we are calculating each frame until we hit that maximum value of 2. So when our delta eventually adds up to 1, we're going to be multiplying 1 times our decreased HP value. So ultimately, we are decreasing our -2 per second. And the reason that we are doing this per frame is so that we can make sure that our health bar is moving smoothly and doesn't kind of stutter with varying frame rates. So if we hop into our add HP method, we can see that we have our added value and we have our final HP value. When we add our HP, we have our maximum HP brought over from our configs, where we will clamp between our current HP 0 to our maximum HP. So our HP will never go below 0 or go above our maximum HP. Then with our final value, we're going to set our HP slider value, so this will be the UI slider, to the current HP. And then finally, if our HP is less than or equal to 0, meaning that we have run out of HP, then we're going to call end main game, which is going to start the game end sequence. It's again going to set the flag is end true, and we saw multiple places utilize this is end flag to make sure that certain things don't happen while the game is over. After our game is over, we are going to stop all other processes, such as our scrolling and other things that depend on our isEnd property. And we're going to show our result pop-up, as well as update our best score. So the UI for our HP bar is going to be located under UI, Toast Group, In-Game UI, and our HP bar. So if you toggle on our UI, and we'll activate this just for a moment, here is our HP slider. And this is a slider from a value of -4 to 100, and if we set this value up and down, let's say to 50, we can see that our slider value also changes up and down as well. So our slider has a value of 0 to 100, and if we adjust and modify this value, let's say to something like 40, we can see that our slider will be adjusted based on this value here. So let's hide this UI and hop back into our code. And if we slide over to our UI manager logic, we can see that we have that set HP slider value that we saw called from our game logic. So here we are going to grab the HP slider, and our HP slider is going to be just the reference to our HP bar under the path that we just looked at. And we're going to grab the slider component, and we're going to adjust that value property, and we're going to clamp this value from 0 to the maximum HP. So this will always be between 0 and maximum of, if we check our config, our maximum HP is going to be 100. And then we're going to return that slider's value. And that's really it for our HP and our stamina logic for auto-decrementing our stamina and ending the game when our stamina hits 0. So let's summarize our entire flow. First, we have a time-based stamina reduction function using the onUpdate and using the delta frame time from our game logic. Second, we have real-time UI synchronization using the slider component. So now we have our own life system, and in this way, our stamina decreases over time, and when the stamina hits 0, our endMainGame method is called and the game ends. However, there's currently no way to display the game has ended to the user. Also, even if you want to restart the game, at the moment there's no way to do so. So in the next section, we're going to take a closer look at the UI system and UI group control, which are responsible for displaying relevant UI to players at the beginning and end of the game. Let's take a look at the core UI that our players will be interacting with in our game. So in our sample world running platformer, the game's progress is shown to the player in 3 main situations: the title screen, the in-game UI, and the result screen that pops up after a level. Now, you might be tempted to manage each little UI element one by one, turning them on and off as needed. But let me tell you, that can get really messy really fast. If you ever need to change the game's flow, and trust me you will, it can be a nightmare to go back and fix everything. That's why I want to show you a much better way. Instead of controlling each element individually, we can use what's called a UI group, which acts kind of like a canvas. This lets us group all the UI for each state and control it all at once. It's a super handy and organized way to manage our UI, and it'll save you a ton of headaches down the road. So let's hop into our UI edit mode, and let's take a look at some of these UI that we had mentioned. So under Toast Group, we can see that we have 3 main entities that are going to serve as the main groups for our UI. So we have our UI title, we have our in-game UI, and we have our result pop-up. So under our UI title, we have our best score panel, we have our UI title for the title of our game, we have the start button, and we have the manual button. Notice the text on these don't really look like the text in our game, but rather look like keys, and that's because they are. If we look at our best score text, you can see that we have the key UI_best score. If we go into our data table here, we can see something called a string table, and this is going to be our localization table. So here we have our UI best score, and we have our Korean version and our English localized version. So our UI best score is going to act as a key to grab the proper localization of our text. So going back to our scene, if we look at the UI best score text and check its property, we can see that we have is localization key toggled on. This will mean that it'll check for any localization tables that exist in our project, and if it does, it's going to check if this key exists and grab the proper localization for our language. Now let's hop off of UI mode, and remember that our UI manager logic handles the main flow of our UI. So in our UI manager logic, we can see that we have all of these connections being made in our connect references, and we're going to search for all of the entities that are within each group. So whether it's within the UI title, the in-game UI, or the UI results groups. We also have mobile specific buttons like our button jump and button slide for the mobile environment, but beyond that, most of our UI is going to be grouped into these 3 sections. Once we've connected all of those references, we're also going to register our button click event listeners for our result to menu button and our title game start button. When our result to menu button is clicked, we're going to return to our main menu from the game, and our title game start button is going to show the character select pop-up, and after selecting a character, you can begin the game. One warning that I'll make with this connect references approach is that because we are searching by a specific path, you have to be careful of typos And we also have to be careful of swapping parents or locations of these entities, as they will break our references. So please be mindful that if you are utilizing this runtime reference connection approach, that you do make sure that you are properly setting the correct path text. And if you do change after the fact, to remember to go back and change these references. So in our title UI, we also have a best score value. And if we check our UI manager logic, we can see that our update title best score is the method that actually updates this score text. So if we have a score value, then we're going to assign the best score text to the score. And if we remember from our game logic, we have our load data method that is called whenever the user enters into the world, where we load in our user data. In this case, it's just going to be the best score, and that's the only data that we are loading from our global data storage at the moment. And once we update this best score value, we are checking for the onSync property for this property. And when it's changed on the server, we're going to update our client and update our UI and call that update title best score. Our UI manual has its own controller where in onBegin play, we hook up our UI manual pop-up to the UI manual path. And then we also have our close button also being hooked up here. And then when we click on the manual button, we show our pop-up, which is going to enable our manual pop-up, which is just going to be this entity right here. And then our close button is just going to hide our pop-up. And that's everything for our title screen. Moving on to our in-game UI, when we start the game, we can notice a couple things. We have our score UI up at the top. We have our health UI that we just took a look at. And we have that countdown timer, 3, 2, 1, before the game starts. So let's take a look at all of those and see how they are managed through our UI manager logic. So starting with that score text, we have our UI manager logic set score text, which is going to assign the in-game current score text value to the value that we pass in. This value is set from our game logic. And if we check our set score method, we can see that our UI manager logic set score text that we just looked at is called from this set score method from within our game logic. Similar to the HP decrease UI that we took a look at, we also have an auto increase score. So every frame, we're going to increase our score at a given interval. So if we check our auto increase score method that is called every frame and passed in our frame delta, we can see that we have a score increase timer that is being accumulated by our delta value. Then we have our config's increase score interval, which is going to determine how often we increase the score value. Above that, we have our increase score value that will determine how much to increase our score at this given interval. So back to our game logic, we can see that if our score timer is less than our increase score interval, then we're just going to simply accumulate that delta and return. Otherwise, we're going to add the score by the increase score value that we saw in our config. Then we're going to reset our timer back to 0 so that at the next interval, we can increase the score again. As for the countdown timer, inside of our game start method that begins our game and initializes all of the sequences required, we have at the end our countdown timer start method. If you look into this method inside of our UI manager logic, we can see that we have our countdown timer text being set to 3, waiting 1 second, and then setting it to 2, waiting 1 more second, and then setting the text to 1. And then finally, after the final second, we're going to set the counter text entity enable status to false and hide our counter. Once that timer is complete, then we're going to set the isEnd property to false. This wait method that we see in our countdown timer is called a synchronous execution, where we are pausing the execution of our current logical flow for this timer. So that means that when we call countdown timer start, we are stuck at this line until the countdown timer is fully complete, after which our isEnd flag will be set to false, beginning the scroll and other things that depend on isEnd flag to be set to false. And that takes care of our in-game UI. Finally, we're going to take a look at our result screen. After we fail the game, we are given this result screen that shows our best score and our current score, and the option to return to our main menu. If we go back to our UI manager logic, we can see that we have a show result pop-up. This result pop-up will set our result best score text to the best score value and our current score text to the current score value, and then enable the pop-up status. This result pop-up is called from game logic, and if you remember, when our stamina hits 0, it will call our end main game. So here in our add HP, when our HP hits 0, we call end main game, and from here, we call the show result pop-up, where we pass in the best score value and the current score value. Back into our UI manager logic, if we go all the way up to our init method, we can see that we have our return to menu button that will call return to menu when this button is clicked. So when we do return to menu, we hide our player info, and we are going to set the character select pop-up enabled to false. We're going to set the result pop-up to false, and we're going to re-enable our main title UI. Our show player info method, based on the active boolean parameter, is going to set the HP slider, the in-game score text, the skill render, etc. to the active or inactive status, depending on what we pass in. And there you have it. We've officially built a solid system that switches our UI based on the game state, all managed by our UI manager logic. The structure we just created is super powerful, and you can use it to manage even the most complex UIs you can dream up. I really encourage you to play around with what you learned today, because you now have a great foundation for building any kind of game UI you want. So let's take a look at our game UI again. The character runs and the health goes down, but it feels a little bit too safe. There are no actual threats out there to keep our players on their toes. Well, in this next section, we're going to learn about how we spice things up by implementing an obstacle system to add some real tension and challenge to our game. So the obstacle system we've implemented is divided into 3 major steps. First, placing the obstacles. Second, detecting collisions. And third, reducing health. Let's take a look at the models for our tiles. If we open up our first tile set, model_tileset01, we can see that we have an obstacle parent here. Underneath this obstacle parent, we have several obstacles that we have preset into the tile. So we have this first obstacle, we have this second obstacle, third, and then our fourth obstacle over here. Let's disable all of those for now. And the way that our logic will work is that we will randomly enable or disable these tiles depending on a random chance. So on a 50% chance, we will enable a certain tile. There's a chance that all of these will be enabled altogether, or some of them will be enabled and others will be disabled. So this way, every time this specific tile is spawned, it seems a little bit different every time. And because these obstacles are a child of our tile chunk, it will move smoothly along with our tile chunk and not have to be separately moved. Now, if we open up our tile set component, we can see that we have a spawn obstacles method. And within here, we are grabbing that obstacle parent and we're getting the children count. And for each of the children, we're going to randomly generate a number from 0 to 1. If the number is 0, we're going to activate it. Otherwise, we're going to deactivate it. If we are activating the entity, we're going to set the visuals, the sprite RUID, to the current stage's obstacle RUID. And the spawn obstacles method is called in our init method. So whenever this tile is created from our pool, we're going to be initializing this entity, if you remember, in our object pool section. And in our init, we have our spawn obstacles that is being called. Next up, when the player makes contact with this obstacle, the player has to take damage. So for that, let's hop into our custom player controller. Inside of here, let's scroll all the way down to the bottom where we can see our handle trigger enter event. And we're going to be grabbing the trigger group by getting the trigger body entity's trigger component, the collision group, and the ID. So effectively, what this will be grabbing is this right here. So in each obstacle, we have a trigger component. Let's enable one and take a look. We can see that there's this green area here where we can detect collisions. So here we have our collision group that is going to determine whether or not different entities can actually collide with each other and detect collisions. So that will be determined by our collision matrix. We can see that our player does in fact collide with our obstacle by this check mark here. So hopping back into the code, in our trigger entry event, we're going to grab that ID and check if it's an obstacle. If it is, then we're going to call the contact obstacle method. From within this method, first check if we are currently invincible. If we're not, then we're going to subtract the obstacle damage. So our config file has the obstacle damage. So every time we take damage, we're going to decrease our health by 5 or stamina by 5. And we're going to set the is-hit flag to true and set our invincible time. This invincible time will make us invulnerable to damage for this timer. So our invincible time is set to 1 second. So for 1 second, we will be invulnerable to damage. Then we're going to play the damage effect, and we're going to set the avatar's transparency to 0.5 to make it semi-transparent to convey that we're currently invulnerable. If we hop up to our update method again, or hop down rather to our update, we can see that once our invisible timer has fully elapsed, then we're going to set our is-hit property to false, and we're going to reset our alpha back to 1. Alright, so let's recap what we just built. When you play the game now, you'll see that hitting an obstacle correctly drains your health, and you even get that brief moment of invincibility afterwards. We've successfully created some real tension that forces players to actively jump and slide to survive. But you might have also noticed a problem. With health constantly draining and dropping drastically when you hit something, the game feels a little unfair. So no matter how skilled you are, you won't last very long before it's game over. Well, we're gonna fix that. In the next section, we'll give our players a fighting chance by implementing an item system that can restore their health and keep them in the game a little bit longer. This time around, let's implement a fully fledged item system. Now, in the previous section, we've already did some prep work by setting up the basic data for our items, but now it's time for the fun part, making them actually appear in the game and have an effect when our character picks them up. So here's the game plan. First, we need to figure out how to spawn items into our game world. Next, we have to detect when our character actually collides with one of those items, and once they do, the item will pass the information over to our item logic. Finally, the item logic will figure out what kind of item it is and trigger the right effect, like restoring health, for example. And here's our little secret. The whole process is going to feel very familiar. It's almost the exact same logic we use when we implement the character's skills with skill logic. So if you understood that part, you'll pick this up in no time. Let's dive in. First up, let's review our dataset process. So we have our data table and we have our item info. We have coin, health, and booster effects, and we're going to load those into our dataset logic. So here we have our item info table and we have the init method for our item info. We're going to load each of those columns into a row data, and we're going to access them by the key for name, RUID, value, spawn rate, and entry ID. Having this data stored in and cached into our item info table will allow us to easily access our item information from our dataset logic whenever we want to and from wherever we want, because our dataset logic is globally accessible. So how are these items placed? Well, let's take a look at our model one more time and double click to open up our tile set. So we went over our obstacles already, and we mentioned that our obstacles are pre-placed into our tile chunk. Our items are similar, but a little bit different in its function. While our obstacles are pre-placed and randomly activated and deactivated, our items are simply locations for our items to be spawned at. This can be different items depending on their spawn rate. So if we go back to our item info table, we have a spawn rate of 1 for a coin, we have 0.03 for a health, and 0.05 for a booster. So depending on the chance, we can place an item at that location. So more often than not is of course going to be a coin, because there's a higher chance of an item being a coin because of the larger ratio that our coin takes up compared to our other items. However, at a given chance, we can still spawn a health or a booster. So again, our item parents are simply locations for spawning our items, and we're of course going to be utilizing our object pool to pull items from our object pool and making sure that we are not destroying and spawning our items in at runtime. First up, let's initialize our item pool because we are going to be utilizing our object pool logic. So before we get into the object pool logic, first let's take a look at our config file and notice that we have our item pool init count, and we have that set as a value of 5. Our item pool init count in our config will determine the initial number of item objects to create in our object pool. So what this means is that we will be pre-spawning these items so that we don't have to spawn those in at runtime. So remember in our object pool logic, when we try to retrieve an item, we're going to first check if the item exists. So we have our item pool and we're going to pass in our item name as a key, and that will return a table of our available item entities. If that target table's length is 0, then that means we don't yet have any items to recycle. So in that case, we're going to create a new item. So we are going to be spawning a new item in that case. But after that, we're going to be recycling that item over and over again until such time that we have no more items available in our pool, and we're going to be creating a new item in that case. But at the start of the game, we can prepare for this in advance by spawning a number of items to the pool in advance. So we're going to be spawning 5 items in advance to our pool. Going back to our object pool logic, also notice that we have our item dataset table, which will map a string to a certain index. So a coin will have an index of 1, a health will have an index of 2, and booster will have an index of 3. And this allows easy access to our item pool so that we can quickly retrieve those by the name rather than a certain index. So remember, in our game logic, we have our initializing sequence in our order init, where we initialize our object pool. This is going to be where we initialize those 5 items to our pool. So remember, in config, we have an init item pool count of 5, and we're going to be initializing that here. So inside of our initialize method of our object pool logic, we can see that we have the init item pool method being called. From there, we're going to be creating a number of items based on the pool init count. So for the coin, health, and booster items, we're going to be creating 5 of each of those items because the value of this will be 5 from our config. So when we create this item, we're going to be passing in the item name. We're going to grab the dataset ID. Remember, that is mapped to this ID here. So coin 1, health 2, and booster 3. And we're going to grab that dataset entry, whether it's a coin, a health, or a booster, and we're going to grab the entry ID, the name, and the value for that data. We're then going to validate this pool to make sure that we actually have a table. If it hasn't been initialized yet, we're going to initialize our table to an empty table, and we're going to set the item pool based on the name to the temp table. Otherwise, we're going to set our temporary table to the corresponding table, whether it's a table for the health, the coin, or for the boosters. Once we have that table, for as many as we are passing in the create count, we're going to be spawning a new item. So we're going to be spawning that model based on the entry ID, and remember that will be this right here, and that gives us a reference to our model. And we're going to be caching that into our item pool parent so that we can use this in our logic later on. So this pre-spawns 5 of each of the type of coin, health, and boosters into our pool so that it can be used in our game. And again, when we get the item from our getItem method, we're simply going to again check for that item pool and then return the target entity that we retrieved from that pool. When we return an item, we're going to be returning that entity, whether it's a health, coin, or a booster, back to the pool. And to do this, we're going to be grabbing the item name based on the name property of the item component of our entity. And we're going to insert the entity into our item pool based on that item name. And then we're going to attach this as a child of our item pool parent, and we're going to deactivate this entity. So now that we have our pool set up, we're going to actually spawn the items into our tile set. So in our tile set method, we have that init method again. And first we're going to return all the items. So that will grab all of the items and return them back to the object pool using that return item method that we saw earlier. And then we're going to spawn item. So our spawn item method is going to grab all of the children of our item parent. So remember, in our tile set, we have these item parents right here as spawn locations for all of our items. And for each of those, we're going to grab and calculate the spawn rate. And depending on the spawn rate, we're going to grab the relevant entity from our object pool. So that will be the health, the booster, or the coin, depending on the corresponding spawn rate. After we've grabbed that entity, we're going to attach that as a child of the location, and we're going to set the local position to 0. So it'll be childed to this location entity. Setting the item's position to 0 will align that entity, because it's a local position, to our location entity. Now that we've got our object pool and we've got our spawning set up, Let's take a look at what happens when the player actually collects the item. If we could hop back into our maker here, we can see that we have these 3 items. So we have our booster item, and we have a trigger component that has a collision group of item. And if we open up our collision matrix, we can double check to make sure that our item does in fact collide with the player. So now that we have that set up, we can go back into our custom player controller, and all the way down into our handle trigger event, we can again check for the group of item. So we're again grabbing the collision group, and that will be this item collision group here. And then we're going to check if that collision group matches item. If it does, we're going to call contact item, and we're going to pass in the trigger body entity's item component. So that will be this component here attached to this model booster, coin, or health. So when we hop into our contact item method, we can see that when we collect it, we're going to play the sound, and then we're going to check for the item's name, whether it's a coin, health, or a booster. And depending on what type of item it is, we're going to add score for the coin, we're going to add health for the health, and we're going to use booster for the booster. So in our item logic, we have a use booster method. And if we enter into here, we can see that we are grabbing our boost duration from our config file, and we're going to increase the speed of our scrolling by that boost item factor. So we talked about this briefly during our scrolling section, but just reviewing that here for our use booster method, that will increase the scrolling speed of our background and the tile sets. Now there's an important condition here. We are multiplying our default speed by our boost item factor, and we're going to assign that to the target scroll speed, but we don't want our booster to overlap. So if the booster is already true, then we're just going to allow the boost timer to reset to our boost duration, and then just return out of this logic and not have to re-execute all of this logic over again. So in this way, we can just simply reset the booster timer without having to activate all this logic over again. And remember, once our boost timer is done, then we're going to reset our scroll speed and our background scroll speed back to its default values. And there we have it. We've successfully added a simple probability-based item spawning system. And you can now control the whole feel of the game just by tweaking the spawn rate. We've got the health packs to heal our player, coins to rack up the high score, and a booster for that satisfying burst of speed. By combining this with object pooling, we've created a smooth, lag-free, and really fun endless runner. But let's think about this for a second. Imagine you're having a great run and you set an amazing new high score. What happens if you close the game and come back tomorrow? Yep, all that hard work is gone. Your high score vanishes and you're right back at 0. That's not exactly what we want for our player. So in this next section, we're going to fix this by building a data storage system. This will allow us to save and retrieve important data, like the player's valuable high score, so it's always there when they come back. Okay, so we're at the last stretch here, and we're going to finally, as the last part, we're going to implement a saving and loading system of the player's highest scores. So we'll make it so that the highest score remains the same even if you close the game and reconnect. Let's take a look at the entire process first. When the game's over, the current score is compared with the highest score, and if it's a new record, it's saved and then loaded the next time you log in and displayed on the title screen. So first up, let's hop into our game logic and scroll all the way to the top and notice that we have our best score property here. This best score property has a sync tag associated with it. And what this means is that whenever this value is adjusted from the server side, it will be automatically updated to the client side as well. So we have a server version of this value and we have a client version of this value. Having the sync tag gives us the peace of mind of knowing that the client and the server will always be synchronized with each other without having for us to manually synchronize those values. So from the server side, when we call load data, we're assigning our best score property. Remember, that is that synced property up there. We're going to assign that to the loaded data from our global data storage based on the key best score. So when we load that in and assign that to our best score, it will update the server copy of our best score property. And then it'll send a message down to the client to update our client version of our best score. And when that happens, we have our onSync property method that is called, and we can then listen in on that best score property name and then call UI Manager logic and update the best score in our main menu. So now that we know what that sync property does, let's review the full process for what happens and the logical flow for loading in our data and saving our data. So when the user enters our world, we call load data. This will, again, load in our data and save it to our best score, which will then update the UI on our title menu with the best score that was loaded in. If the best score was never set, then the best score will of course be 0. Then, while playing the game, we have our score being automatically increased by our auto increase score that we reviewed, and we're going to be increasing that score periodically. So as we increase the score, we have our current score being increased by that value. And then when the game ends, we're going to set our best score to the current score. And then we're going to call update score, which will set the best score on the server side to the score value that we pass in. And again, remember, because we're setting it from the server side, it will also update the client side. And when we do so, we're going to listen in on that event by listening in on the onSync property method. And then we're going to update the UI on our title with that new value. Let's hop all the way down to the bottom of our code. And when the user leaves the game, we're going to call save score. So every time the user leaves the game, we're going to save our current best score value that was saved. So this means that if the user leaves at the middle of the game, it will not update because the best score only updates after the game is ended. So in our end main game, the best score value is set to the current score only after the game is fully ended. So when the user leaves, we're going to call save score. And in this save score, we're going to grab our global data storage and we're going to set the best score key to the score value. One special note that I want to make is that the reason why we are using onSync property to listen for the exact moment that the server communicates the new best score value to the client is because there may be a slight delay in between when the server sends the message and when we try to retrieve that value. So let's say we set our best score on the server side. So we've called update score and we've updated our best score. Then we transition back to the main menu, and before the server has the chance to finish communicating the score value to the client, we have tried to retrieve that score. The score will remain at the previous state because it will change, or it may change, after the client has a chance to read the value from the server. So here we have an issue of execution order. So to mitigate that, we are using onSync property to make sure that we update the title best score at the exact moment that the client receives the message from the server to update our best score value. This way, we don't have an issue of fighting for or checking for that best score value and making sure that we update the best score only when the client has actually been updated from the server side. And just like that, we're done. We've created a really efficient system that saves the player's high score to the server and loads it right back up, so they never lose their progress. Let's take a step back now and take a look at everything we've accomplished together. We've built a complete simple running platform from the ground up. We've established an entire framework of the game out of 3 core managers: game logic, UI manager logic, and dataset logic. Using these 3, we've created a smooth, endless optimized world using procedural generation and object pooling. We brought our character to life, gave them skills, and added obstacles and items to them to make it feel genuinely fun and challenging. The best part is, while we use the methods here in our sample Infinite Runner world, you now have all the tools and concepts you need to go out and build your own unique and creative, amazing running game. I truly hope this tutorial series has been a huge help and that it gives you the confidence you need to take your own ideas and turn them into a reality. Thank you so much for watching and happy developing!